A single bit of information switched in 40 trillionths of a second. Not once. 100 billion times in a row, without failure, without breaking down, without generating the wave of heat that would have destroyed almost anything else humans have ever built at that speed. Meanwhile, on the other side of the planet, a separate team just found a way to make ordinary chips talk to each other 100 times faster, using a fraction of the power by replacing electricity with light. Read that again. 2 different teams, 2 different continents, 2 entirely different pieces of physics, both converging within weeks of each other on the exact same brutal problem that has quietly limited every computer you've ever owned. To understand why these breakthroughs matter enough to justify a title this dramatic, you first have to understand the single, stubborn law of physics that has shaped nearly every decision chip designers have made for the past 50 years. Heat. Every time a computer chip processes information, it generates waste heat as an unavoidable byproduct. And the faster you try to push that chip, the more heat it produces, until eventually the chip either slows itself down to survive or simply burns out entirely. This isn't a minor engineering inconvenience. It's arguably the single biggest reason computers, phones, and data centers cannot simply keep getting faster forever, no matter how much money gets poured into research. More speed has always meant more energy loss, more elaborate cooling systems, and more wear and tear grinding down expensive hardware. For decades, companies like NVIDIA, Intel, AMD, and Apple have focused enormous engineering effort on making chips smaller and faster. But they've always run headlong into the exact same wall. Faster chips create more heat, and more heat eventually makes faster chips impossible, a physical ceiling that no amount of clever marketing has ever managed to fully erase. This is precisely the wall a team of researchers at the University of Tokyo set out to attack directly. And their approach, published in the prestigious journal Science in the spring of 2026, doesn't try to squeeze more speed out of the same old approach to computing. It abandons that approach entirely. Instead of representing a single bit of information using the continuous flow of electrical current, the method every modern chip has relied on. Since the earliest days of computing, the Tokyo team built something they call a non-volatile switching element, a device that stores information using the magnetic properties of individual electrons instead. Think about why that specific change matters so much. Electrical current, by its very nature, generates resistance as it flows. And resistance generates heat, an unavoidable tax charged every single time a chip does anything at all. But magnetism works differently. A magnetic state can be flipped, read, and stored without depending on a constant stream of current running through the device, sidestepping the exact physical mechanism responsible for most of the wasted heat plaguing conventional electronics. The materials behind this breakthrough deserve their own moment of attention, because the specific combination the researchers chose reveals just how carefully engineered this solution actually is. The device is built from ultra-thin layers of tantalum, a tough, heat-resistant metal capable of storing and releasing electrical charge, layered together with a compound called M3SN, a mixture of manganese and tin that happens to be antiferromagnetic. That specific property matters enormously. An antiferromagnetic material maintains genuinely stable magnetic properties and resists interference from outside magnetic fields, precisely the kind of stability you'd want if you were trying to build a switch reliable enough to survive billions upon billions of operations without drifting or degrading. And the speed numbers this combination produced are, frankly, difficult to fully process on an intuitive human level. The device switched a single bit of information in just 40 picoseconds. To put that number in perspective, a picosecond is 1 trillionth of a second, meaning the entire switching operation completed in a span of time so brief that light itself, the fastest thing in the entire universe, would travel only about 12 millimeters during that window, roughly the width of your fingertip. Conventional chips, by comparison, typically require somewhere around 1 full nanosecond, 1,000 times longer to record a single bit, and they start running into serious overheating problems as they approach even that comparatively pedestrian speed. Here's where the story moves from impressive laboratory physics into something that starts to feel genuinely practically significant. Speed alone means very little if a device can't survive being used repeatedly under real-world conditions, and this is exactly where the Tokyo team's results become almost startling. In controlled laboratory testing, their device processed information successfully for more than 100 billion switching cycles without a single failure. Read that number again, slowly. 100 billion. For comparison, conventional chips operating at anywhere close to similar speeds would typically be expected to fail after roughly 10 million cycles, as accumulated heat damage finally overwhelms the material. That means this new device demonstrated durability roughly 10,000 times greater than what conventional technology could achieve running at comparable speeds. This is not chaos. This is exactly the kind of overwhelming, almost stubborn evidence a genuinely new approach needs to provide. before serious engineers will take it seriously, proof that the underlying physics doesn't just work once under perfect laboratory conditions, but survives the kind of relentless, repeated abuse any real-world chip would actually experience inside a working computer. And there's one more detail buried inside this research that deserves particular attention, because it flips a long-standing assumption in chip engineering completely upside down. For most conventional chip technologies, shrinking a component down to smaller and smaller physical dimensions tends to make heat management dramatically harder, not easier, because you're cramming the same amount of electrical activity into an increasingly cramped physical space with less room for that heat to safely dissipate. The Tokyo researchers report the exact opposite trend for their device. Performance actually improves as the components get smaller, raising a genuinely tantalizing possibility for the future of this technology, that continued miniaturization, the same relentless drive towards smaller, denser chips that has defined the entire semiconductor industry for decades, could work in this technology's favor rather than against it, potentially reducing energy consumption even further as engineers eventually learn to shrink these devices down toward truly microscopic scale. Now, before this story tips over into uncritical excitement, it deserves exactly the same honest, grounding scrutiny we bring to every breakthrough covered on this channel, because understanding the genuine limitations here matters just as much as understanding the genuine achievement. This technology remains, as of right now, firmly at the laboratory demonstration stage. The University of Tokyo team has proven rigorously and repeatedly that the underlying physics genuinely works, and that their specific device can survive far more punishing, repeated operation than anything conventional electronics could tolerate at similar speeds. But proving a concept works inside a carefully controlled university laboratory is a fundamentally different challenge than transforming that single successful device into something a manufacturer can reliably and affordably build at genuine industrial scale across millions or billions of units with consistent quality and acceptable cost. That transition involves an entirely separate universe of hard, unglamorous engineering problems, manufacturing processes, supply chain logistics, financing, and distribution, none of which have anything to do with the elegant physics that made headlines in the first place. According to the researchers' own stated timeline, a working prototype chip built around this technology isn't even planned until the year 2030, which means genuine commercial availability, the kind of product an ordinary consumer could actually purchase, would realistically arrive years after that, quite possibly well into the following decade. This is not a next shopping cycle upgrade. It's a meaningful, genuinely exciting signal that lower power, ultra-fast computing may eventually be possible. But the distance between today's laboratory result and tomorrow's actual product remains genuinely, honestly substantial. Think about what success would actually mean, though, if this technology genuinely does clear all those remaining engineering hurdles over the coming years, because the practical implications extend directly into problems dominating headlines right now. Artificial intelligence has triggered an explosion in global computing demand, unlike almost anything the technology industry has ever seen before. Training today's most advanced AI models requires enormous data centers packed with power-hungry graphics processors running continuously around the clock, and those facilities already consume staggering, genuinely difficult to comprehend amounts of electricity. Cooling all of that hardware has become an increasingly expensive, increasingly urgent problem in its own right, a massive secondary cost layered directly on top of the raw electricity needed to run the chips in the first place. Or, if magnetic switching technology like this eventually becomes genuinely commercially viable, it could dramatically lower the total amount of energy future AI systems actually need to operate. In theory, future processors built around this exact approach could use only a small fraction of the power consumed by today's most advanced chips, while simultaneously running significantly faster. Faster computing with dramatically less wasted energy could eventually translate into laptops running for months between charges, rather than mere hours, and downloads that currently take an entire hour to complete could theoretically finish in a matter of seconds instead. That's the genuine, if still distant, promise sitting inside this specific breakthrough. While this research was making headlines out of Tokyo, an entirely separate team on the other side of the world was tackling a related but distinctly different piece of the same underlying puzzle, and their solution took a genuinely different form. In July of 2026, researchers at Peking University published results in the journal National Science Review describing a new all-optical interconnect system, and understanding exactly what problem this specific breakthrough solves requires shifting your attention away from individual transistors, switching on and off, and towards something equally important but far less discussed: how chips actually talk to each other once you need more than one of them working together on the same problem. The team's corresponding authors, Professor Xu Haowen and Professor Wang Xingjun, weren't trying to build some exotic, never-before-seen chip from scratch. Their genuinely clever insight was recognizing that the industry's conventional response to rising AI computational demand, the endless cycle of piling on more and more graphics processors and building ever larger, ever hungrier data centers, represented a kind of computational brute force that couldn't realistically scale forever. Instead, they asked a different, more targeted question. What if the real bottleneck wasn't the individual chips themselves, but the sluggish, inefficient way those chips were forced to communicate with each other? The building blocks the Peking University team actually used deserve genuine attention, because their choice reveals a refreshingly pragmatic approach to solving this specific problem. Rather than inventing exotic new silicon from scratch, they built their system around field-programmable gate array chips, commercially available, already widely deployed hardware used across industries that demand serious parallel processing capability, everything from missile guidance systems to autonomous vehicles to ordinary data centers. Think of these FPGA chips as the team's building blocks, genuinely capable individual pieces of hardware that, on their own, weren't the actual bottleneck holding back overall system performance. The real innovation lives specifically in what the researchers described as the joints connecting these chips together, two custom-designed communication components engineered specifically to replace slow, heat-generating electrical connections with light itself. The first of these components is a silicon photonic transceiver chip, operating at an extraordinary 400 gigabits per second, responsible for converting electrical signals into optical signals and then converting them right back again, allowing separate chips to exchange enormous quantities of information using beams of light traveling at, quite literally, the speed of light, rather than electrical current, crawling comparatively slowly through copper wiring. The results this specific approach produced are genuinely striking and worth stating precisely, because the exact numbers matter enormously here. By optically linking standard chips together using this new interconnect system, combined with specifically designed algorithms built to take advantage of it, the Peking University team demonstrated a boost in AI distributed inference speeds by a factor of over 100 times, while simultaneously slashing the computational resources required down to just 1/9 of what conventional approaches typically demand. Read that combination again, because it's genuinely remarkable when you consider both numbers together rather than separately. Not simply faster, at the cost of burning through more electricity to get there, the way brute force computing scaling almost always works. Genuinely faster, while requiring dramatically less computational overhead to actually achieve that speed. This directly attacks the exact pattern the researchers themselves criticized as the industry's conventional, unsustainable playbook, the seemingly endless race to pile on more raw hardware and more electrical brute force, rather than fundamentally rethinking how existing hardware actually communicates and cooperates. There's a genuinely exciting, if considerably more speculative, extension of this same underlying idea worth exploring here, because it points toward an entirely different possible future for how computer chips might eventually be manufactured altogether. Industry analysis following the Peking University publication has floated the concept of what some are calling a macrochip. An approach where, instead of manufacturing a single enormously complex chip using extraordinarily expensive extreme ultraviolet lithography, the same process powering today's most advanced silicon, manufacturers could instead imprint hundreds of smaller, individually simpler microchips, sometimes called chiplets, directly onto a single large silicon wafer, potentially 8 or even 12 inches wide. Rather than relying on the traditional internal wiring and clock timing that has governed chip design for decades, these individual chiplets would communicate with each other at the literal speed of light, using exactly the kind of optical interconnect technology the Peking University team just demonstrated. Some more ambitious projections built around this concept suggest that a fully realized version of this macrochip approach could eventually deliver something in the neighborhood of 1,000 times the raw computing power of today's most powerful individual graphics processor. This is where honest reporting absolutely has to draw a clear, firm line, though. That specific 1,000 times projection remains speculative industry extrapolation, an exciting possibility being discussed by analysts following this research, not a verified, peer-reviewed result the Peking University team actually demonstrated and published themselves. The 100 times inference speedup and the 90% reduction in compute requirements are the genuine, published, peer-reviewed achievements. The broader macrochip vision remains a compelling, plausible, but still unproven extrapolation of where this underlying technology might eventually lead if a whole series of additional engineering challenges get solved successfully over the coming years. Stepping back from either individual breakthrough for a moment, it's worth appreciating just how remarkable it is that these two genuinely separate, entirely independent research efforts emerged within roughly 2 months of each other, tackling what amounts to two complementary halves of the exact same fundamental problem. The University of Tokyo team attacked the heat and speed limitations sitting inside individual transistors themselves, the basic building blocks every modern chip is ultimately constructed from. The Peking University team attacked the communication bottleneck sitting between separate chips once you need multiple processors working together on a shared computational task. Neither breakthrough alone solves the entire challenge facing modern computing, but together they sketch out a genuinely coherent, genuinely exciting picture of where serious engineering effort is currently being concentrated across the entire global chip industry right now, attacking heat and speed limitations from multiple directions simultaneously, using entirely different underlying physics in laboratories separated by thousands of miles, and, quite plausibly, no direct coordination or awareness of each other's parallel efforts. This pattern connects to something broader worth understanding about how genuinely transformative technology tends to actually emerge in the real world, rather than the way it often gets portrayed in more sensationalized coverage. Revolutionary breakthroughs rarely arrive as a single, isolated, world-changing event. One lab, one paper, one moment where everything suddenly changes overnight. They tend to arrive as exactly this kind of scattered parallel convergence, multiple independent teams, working on related but distinct pieces of the same underlying problem, each contributing a genuine, verified, peer-reviewed piece of the eventual solution, without any single group possessing the complete picture on their own. Consider IBM's own contribution to this same broader wave of 2026 chip research, a design the company calls nanostack, packing an almost unbelievable 100 billion individual transistors into a footprint smaller than a single nanometer, using a three-dimensional stacking approach, rather than the traditional flat two-dimensional chip layout the industry has relied on for decades. Professor Alan Woodward, a computer scientist at Surrey University with no direct financial stake in IBM's specific commercial success, offered a genuinely vivid comparison to help make sense of the scale involved. IBM's nanostack, he explained, is like proposing a 100-story skyscraper while the company's closest competitors, firms like Intel and Samsung, are currently building something closer to a 30 to 50-story building by comparison. In IBM's own internal testing, the design demonstrated a 50% performance improvement and a 70% gain in energy efficiency compared to the company's existing 2-nanometer chips, alongside a 40% improvement in how efficiently the chip's own onboard memory scales. And exactly as with the University of Tokyo's device, IBM is candid about the genuine distance still separating this achievement from any real-world product, estimating that actual production could begin within 5 years at the very earliest. There's a third thread worth briefly acknowledging here too, because it reveals just how broad this current wave of thermal-focused chip research genuinely is, extending even into territory that sounds almost like the opposite problem. Researchers at the University of Southern California, publishing their own results in the journal Science in March of 2026, unveiled a memory device engineered specifically to keep functioning reliably at temperatures reaching 700 degrees Celsius, roughly 1300 degrees Fahrenheit, a temperature that genuinely exceeds molten lava. Led by Professor Joshua Yang, the team's device showed absolutely no signs of failure even at that extreme temperature. And remarkably, 700 degrees wasn't even the device's actual breaking point. It was simply the maximum temperature their available testing equipment happened to be capable of reaching. Think about how this fits into the broader story unfolding across this entire video. While teams in Tokyo and Beijing were racing to eliminate heat from computing entirely, engineers in Los Angeles were simultaneously solving the opposite end of the same fundamental challenge, building electronics specifically designed to thrive inside extreme heat rather than avoid it altogether, useful for applications like deep space exploration, geothermal energy extraction, or industrial monitoring. Inside environments, no conventional chip could ever hope to survive. So, what does all of this actually add up to? Once you step back from any single individual headline and look honestly at the full combined picture, these separate 2026 breakthroughs are painting together. The honest, carefully researched answer requires holding two genuinely true things in your mind simultaneously, without collapsing either one into an artificially simpler, more dramatic story than the actual evidence supports. These breakthroughs are real. They're peer-reviewed, published in some of the most rigorous, most respected scientific journals in the entire world, and they represent genuinely significant, independently verified progress against a problem that has quietly constrained the entire computing industry for the better part of half a century. The University of Tokyo's device genuinely does switch information 1,000 times faster than conventional approaches, while surviving repeated use at a scale that dwarfs anything currently available. Peking University's optical interconnect genuinely does boost distributed AI inference speeds by more than 100 times, while dramatically cutting the computational overhead required to achieve that speed. Neither of these numbers is exaggerated marketing spin. They're the honest, documented, published results of serious, credentialed scientific teams working through exactly the kind of rigorous peer review process that separates genuine breakthroughs from empty corporate hype. But the honest, equally necessary second half of that picture is this. Neither breakthrough is sitting inside a product you can purchase today or even next year, or in the University of Tokyo's case, likely before the very end of this decade. The gap between a laboratory demonstration, however genuinely impressive, and a reliable, affordable, mass-manufactured product sitting inside an ordinary consumer's laptop or an ordinary data center's server rack remains substantial, measured honestly in years rather than months. Turning a single successful device that works flawlessly under a physicist's careful, controlled laboratory conditions into something a manufacturer can build reliably, cheaply, and at truly massive industrial scale involves solving an entirely separate category of hard problems, engineering challenges, financing challenges, supply chain challenges, none of which show up in an exciting research paper's headline results, but all of which genuinely determine whether a breakthrough like this one actually reaches your own hand someday, or quietly joins the long, largely forgotten list of genuinely promising laboratory results that never quite made the difficult, expensive leap into real-world commercial production. What makes this specific moment in 2026 genuinely worth paying close attention to, though, isn't any single one of these individual results in isolation. It's the sheer, unmistakable convergence of so many independent, credible research teams working across completely different countries, completely different institutions, and completely different underlying physics, all arriving at remarkably similar, remarkably urgent conclusions within the exact same narrow window of time. Heat is no longer being treated as simply an unfortunate, unavoidable cost of doing business in modern computing. It's being treated across labs in Tokyo, Beijing, and beyond as a fundamental, solvable engineering problem in its own right, one that a genuinely global wave of serious scientific effort is currently attacking from multiple directions simultaneously. Whether the specific device that ultimately succeeds in reaching your own home computer or your own phone turns out to be built on antiferromagnetic switching, the next major leap forward in computing performance likely won't come from simply making today's existing chip architecture marginally smaller and marginally faster, the same incremental playbook the industry has followed for decades. It's increasingly likely to come from someone, somewhere, finally figuring out how to make computing itself fundamentally, structurally cooler. Widespread commercial deployment inside real AI data centers, that's precisely the story we'll be tracking closely as it continues to unfold. So make sure you're subscribed before either of those milestones finally arrives. Before you go, I want to know what you honestly think about everything you've just heard. Does the sheer number of independent, credible research teams converging on this exact same heat elimination problem within the same narrow window of time feel like genuine evidence that computing is on the verge of a real structural transformation? Or do you think the substantial gap between today's laboratory results and tomorrow's actual purchasable products means we're still many years away from any of this genuinely changing your own daily life? Leave your honest answer down in the comments below. And as always, I read every single one.